Welcome to tonight's journey through the fascinating world of weather patterns. Get comfortable, close your eyes if you'd like, and let's explore the invisible forces that shape our atmosphere, create the clouds above us, and determine whether tomorrow brings sunshine or storms. This is a gentle exploration of meteorology, designed to ease your mind as you drift towards sleep. Weather patterns are the recurring atmospheric conditions that develop over hours, days, or even weeks. They're the reason why certain regions experience predictable seasonal changes, why sailors have relied on trade winds for centuries, and why farmers can anticipate when to plant their crops. At the heart of every weather pattern is the simple fact that our planet receives uneven heating from the sun. The equator receives more direct sunlight than the poles, and this temperature difference sets the entire atmosphere in motion. Warm air rises, cool air sinks, and from these basic principles emerge the complex systems that determine our daily weather. The atmosphere itself is a remarkable thing. It's a thin layer of gases wrapped around our planet, held in place by gravity. If Earth were the size of an apple, the atmosphere would be thinner than the apple's skin. Yet within this delicate envelope, all of our weather occurs. The atmosphere is divided into layers, each with its own characteristics. The troposphere is where we live and where weather happens. It extends about 7 miles above the equator and about 5 miles above the poles. Above that lies the stratosphere, home to the ozone layer that protects us from harmful ultraviolet radiation. Higher still are the mesosphere, thermosphere, and exosphere, but these upper layers have little direct influence on the weather we experience. Air pressure plays a fundamental role in weather patterns. Pressure is simply the weight of all the air above a given point pressing down. At sea level, this pressure is about 14.7 pounds per square inch, though we don't feel it because our bodies are built to withstand it. When air heats up, it expands and rises, creating an area of low pressure beneath it. When air cools, it becomes denser and sinks, creating high pressure. These pressure differences drive the winds that move weather systems across the globe. Air naturally flows from areas of high pressure to areas of low pressure, like water flowing downhill. The greater the pressure difference, the stronger the wind. High pressure systems generally bring calm, clear weather. As air sinks in a high pressure area, it warms and dries out, which discourages cloud formation. You've probably noticed that high pressure often means blue skies and gentle breezes. Low pressure systems, on the other hand, often bring clouds and precipitation. As air rises in low-pressure areas, it cools, and cool air can't hold as much moisture as warm air. The excess moisture condenses into tiny water droplets or ice crystals, forming clouds. If these droplets or crystals grow large enough, they fall as precipitation. The Coriolis effect is one of those invisible forces that shapes weather patterns in ways most people never consider. It's caused by Earth's rotation, and it deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This might seem like a small detail, but it has profound consequences. The Coriolis effect is why storms spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's why winds don't flow directly from high to low pressure but instead spiral around pressure systems. Without the Coriolis effect, weather patterns would look completely different. Jet streams are rivers of fast-moving air high in the atmosphere, typically found where the troposphere meets the stratosphere. These winds can reach speeds of over 200 miles per hour. The polar jet stream, which flows between cold polar air and warmer air to the south, has a particularly strong influence on weather in the mid-latitudes. When the jet stream dips south, it can bring cold Arctic air down into regions that don't usually experience such temperatures. When it retreats north, warmer air flows in. The jet stream isn't a straight line. It meanders in waves, and these waves can become quite pronounced. Sometimes the jet stream develops large loops that can stall weather patterns in place, leading to extended periods of rain, heat, or cold. Air masses are huge bodies of air with relatively uniform temperature and humidity characteristics. They form when air sits over a particular region long enough to take on the characteristics of that surface. A continental polar air mass, for instance, forms over cold land areas and brings cold, dry weather. A maritime tropical air mass forms over warm oceans and brings warm, moist conditions. When different air masses meet, they don't mix easily. Instead, they form boundaries called fronts. A cold front occurs when cold air advances and pushes under warm air. The warm air is forced upward rapidly, often creating towering cumulus clouds and potentially severe weather. A warm front occurs when warm air advances and slides over retreating cold air. This typically produces more gradual lifting and widespread, steady precipitation. Clouds are perhaps the most visible and beautiful expression of weather patterns. They're classified into various types based on their appearance and altitude. Cirrus clouds are high, wispy streaks of ice crystals that often indicate fair weather, though they can also signal an approaching warm front. Cumulus clouds are the puffy, cotton-like clouds that dot the sky on pleasant days. When atmospheric conditions are right, cumulus clouds can grow into towering cumulonimbus clouds, the thunderstorm giants that can reach heights of over 50,000 feet. Stratus clouds form in flat, featureless layers that can cover the entire sky, often bringing drizzle or light rain. Nimbostratus clouds are the thick, dark clouds that bring steady rain or snow. Precipitation takes many forms, all of which begin with water vapor in the atmosphere. Water vapor is invisible. When you see your breath on a cold day or steam rising from a cup of tea, you're actually seeing tiny water droplets that have already condensed from vapor. For precipitation to form, water vapor must condense onto tiny particles in the atmosphere called condensation nuclei. These can be dust, salt crystals from ocean spray, or other microscopic particles. Once water droplets form, they need to grow large enough to fall without evaporating on the way down. In warm clouds, droplets collide and merge until they're heavy enough to fall as rain. In cold clouds, ice crystals form and grow, eventually falling as snow, sleet, or freezing rain depending on the temperature profile of the atmosphere they fall through. Rain is the most common form of precipitation. It develops when water droplets in clouds combine and grow large enough to overcome air resistance. The typical raindrop is about 1 to 2 millimeters in diameter. Larger drops tend to break apart as they fall. Rain can be light and gentle or heavy and torrential, depending on how quickly water droplets are growing in the clouds above. Drizzle consists of smaller drops, less than half a millimeter across, and falls from stratus clouds. Drizzle seems to hang in the air rather than falling decisively like rain. Snow forms when water vapor in clouds converts directly to ice crystals without first becoming liquid. This happens in clouds where temperatures are below freezing. Ice crystals grow into the intricate six-sided shapes we recognize as snowflakes. No two snowflakes are exactly alike because each one follows a slightly different path through the cloud, encountering slightly different temperature and humidity conditions. Some snowflakes are simple hexagonal plates, while others develop elaborate branching structures. The type of snowflake that forms depends primarily on temperature. Sleet occurs when raindrops freeze into ice pellets as they fall through a layer of freezing air near the surface. Freezing rain is more treacherous. It falls as liquid rain but freezes on contact with surfaces that are below freezing, coating everything with a layer of ice. Thunderstorms are among the most dramatic expressions of weather patterns. They require 3 ingredients: moisture, instability, and lift. Moisture provides the fuel for the storm. Instability refers to atmospheric conditions where air, once lifted, will continue to rise on its own. Lift is the initial push that gets air moving upward, which can come from a cold front, a sea breeze, or simply uneven heating of the ground. Once these ingredients come together, a thunderstorm can develop rapidly. Warm, moist air rises and cools, forming a cumulus cloud. If conditions are right, the cloud continues to grow vertically, developing into a cumulonimbus cloud. Within the storm, updrafts and downdrafts create turbulent conditions. Water droplets and ice particles collide, transferring electrical charge. Eventually, the charge separation becomes so great that lightning occurs, which is simply a giant electrical spark that neutralizes the charge difference. Lightning is extraordinarily hot, reaching temperatures of about 50,000 degrees Fahrenheit, which is 5 times hotter than the surface of the sun. This intense heat causes the air around the lightning bolt to expand explosively, creating the shock wave we hear as thunder. Light travels much faster than sound, which is why we see lightning before we hear thunder. You can estimate how far away a lightning strike is by counting the seconds between the flash and the thunder, then dividing by 5. That gives you the distance in miles. Thunder itself is just the sound of air rapidly expanding and contracting. Tornadoes are violently rotating columns of air that extend from thunderstorms to the ground. They're most common in the central United States, where cold, dry air from Canada meets warm, moist air from the Gulf of Mexico. This collision of air masses creates severe thunderstorms capable of producing tornadoes. A tornado forms when winds at different heights blow at different speeds or in different directions, creating rotation in the atmosphere. If a thunderstorm's updraft tilts this rotating air vertical, a tornado can develop. Most tornadoes are relatively weak and short-lived, but the strongest ones, rated EF4 or EF5 on the enhanced Fujita scale, can have wind speeds exceeding 200 miles per hour and can stay on the ground for over an hour, carving paths of destruction dozens of miles long. Hurricanes are massive heat engines that form over warm tropical oceans. They require water temperatures of at least 80 degrees Fahrenheit and form most commonly in late summer and early autumn when ocean temperatures peak. A hurricane begins as a tropical disturbance, an area of low pressure with thunderstorms. If conditions are favorable, the system can organize and strengthen. Warm, moist air spirals inward toward the low-pressure center, rises rapidly, and releases enormous amounts of heat as water vapor condenses into rain. This heat release fuels the storm, causing pressure to drop even further at the center, which draws in more air, creating a self-reinforcing cycle. Hurricanes are classified by wind speed on the Saffir-Simpson scale, which runs from Category 1 with winds of 74 to 95 miles per hour up to Category 5 with winds exceeding 157 miles per hour. The eye of a hurricane is a calm area at the storm center where air is sinking rather than rising. It's typically 20 to 40 miles across and features light winds and often clear or partly cloudy skies. Surrounding the eye is the eye wall, where the hurricane's strongest winds and heaviest rain occur. Spiral bands of thunderstorms extend outward from the eye wall, bringing gusty winds and heavy rain to areas hundreds of miles from the center. Hurricanes weaken rapidly when they move over land or cooler water because they're cut off from their source of warm, moist air. However, even a weakening hurricane can dump tremendous amounts of rain, causing devastating floods. Monsoons are seasonal wind patterns that affect large regions, most famously in South and Southeast Asia. The word monsoon comes from an Arabic word meaning season. Monsoons develop because land heats up and cools down more quickly than water. During summer, the land becomes much warmer than the nearby ocean. Air over the land rises, creating low pressure, and moist air from the ocean flows inland to replace it. This brings the wet monsoon season. During winter, the land cools down more than the ocean, creating high pressure over land. Winds reverse direction, flowing from land to sea, bringing the dry season. The monsoon rains are crucial for agriculture in affected regions, but they can also bring flooding when rainfall is particularly heavy. El Niño and La Niña are opposite phases of a climate pattern in the tropical Pacific Ocean that affects weather worldwide. Under normal conditions, trade winds blow from east to west across the Pacific, pushing warm surface water toward Indonesia and allowing cold, nutrient-rich water to well up along the coast of South America. During El Niño, these trade winds weaken or even reverse. Warm water sloshes back toward South America, suppressing the usual upwelling. This seemingly small change in the Pacific has far-reaching effects. El Niño typically brings wetter conditions to the southern United States and drier conditions to Indonesia and Australia. It suppresses Atlantic hurricane activity but can enhance Pacific hurricanes. La Niña is the opposite pattern, with stronger than normal trade winds and cooler than normal water in the eastern Pacific. La Niña often brings drought to the southern United States and wetter conditions to the Pacific Northwest. The seasons themselves are a fundamental weather pattern, though one caused by astronomy rather than atmospheric dynamics. Earth's axis is tilted about 23.5 degrees relative to its orbital plane. As Earth orbits the Sun, this tilt means that different parts of the planet receive more or less direct sunlight at different times of year. When the northern hemisphere is tilted toward the Sun, it experiences summer with long days and short nights. The Sun's rays strike at a steep angle, concentrating their energy. 6 months later, the northern hemisphere is tilted away from the sun, bringing winter with short days and long nights. The sun's rays strike at a shallow angle, spreading their energy over a larger area. The southern hemisphere experiences opposite seasons because when the northern hemisphere tilts toward the sun, the southern hemisphere tilts away. Near the equator, seasonal changes are minimal because the sun is always relatively high in the sky. Fog is essentially a cloud at ground level. It forms when air becomes saturated with water vapor and the temperature drops to the dew point, the temperature at which air can no longer hold all its moisture. There are several types of fog. Radiation fog forms on clear, calm nights when the ground cools rapidly by radiating heat into space. The air near the ground cools to the dew point, and fog forms. This type of fog is common in valleys and typically burns off after sunrise as the ground warms. Advection fog forms when warm, moist air moves over a cooler surface, such as when warm air from over land flows out over colder ocean waters. The famous fogs of San Francisco and the Grand Banks off Newfoundland are advection fogs. Upslope fog forms when air is forced up a mountain slope, cooling as it rises. Steam fog occurs when cold air moves over much warmer water, causing moisture to rapidly evaporate from the water surface and immediately condense in the cold air above. Dew and frost are related phenomena that occur when surfaces cool below the dew point. On a typical clear night, the ground radiates heat into space and cools down. If the temperature drops to the dew point, water vapor in the air condenses directly onto surfaces as dew. You've probably noticed dew on grass on a clear morning. If the temperature drops below freezing, water vapor can convert directly from gas to solid ice without becoming liquid first, forming frost. Frost creates beautiful ice crystals on windows and plants. It's important to note that frost doesn't fall from the sky like snow. It forms directly on surfaces. Temperature inversions occur when a layer of warm air sits above cooler air near the surface, which is the opposite of the usual pattern where temperature decreases with altitude. Inversions can trap pollutants near the ground because the warm air above acts like a lid, preventing the cooler air below from rising and dispersing. This is why air quality can be particularly poor during temperature inversions in urban areas. Inversions often form on clear, calm nights when the ground radiates heat into space and cools the air immediately above it. They can also form when a warm front passes over an area, sliding warm air over the top of cooler air at the surface. Sea breezes and land breezes are small-scale wind patterns that develop along coastlines. During the day, land heats up more quickly than water. Air over the land rises, creating low pressure, and cooler air from over the ocean flows inland as a sea breeze. You can often feel this refreshing breeze at the beach on a hot afternoon. At night, the process reverses. Land cools down more quickly than water, so the air over the ocean is now warmer. It rises and cooler air from the land flows out to sea as a land breeze. These breezes typically extend only a few miles inland or offshore and reach speeds of just 10 to 15 miles per hour, but they can significantly moderate temperatures in coastal areas. Mountain and valley breezes follow a similar pattern. During the day, mountain slopes receive direct sunlight and warm up, heating the air next to them. This warm air rises up the slope as a valley breeze. At night, mountain slopes cool rapidly by radiating heat into space. The air next to them cools, becomes dense, and flows downhill into valleys as a mountain breeze. These breezes are usually gentle, but they can channel into strong winds if the topography is right. The trade winds are persistent wind patterns that blow toward the equator from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. They were named by sailors who relied on them for trade routes across the oceans. The trade winds are part of the Hadley Cell, a large-scale atmospheric circulation pattern in the tropics. Warm air rises near the equator, flows poleward at high altitude, then sinks around 30 degrees latitude and returns toward the equator at the surface. The Coriolis effect deflects these surface winds, creating the trade winds. Between the northern and southern hemisphere trade winds lies the Intertropical Convergence Zone, or ITCZ, a band of low pressure where the trade winds meet. The ITCZ is characterized by thunderstorms and heavy rainfall and migrates north and south with the seasons, following the sun's most direct rays. The westerlies are prevailing winds in the mid-latitudes that blow from west to east. They're found between about 30 and 60 degrees latitude in both hemispheres. These winds are responsible for the general west-to-east movement of weather systems across the United States, Europe, and other mid-latitude regions. The westerlies are also part of a large-scale circulation cell called the Ferrel cell, though the Ferrel cell is more complex and less defined than the tropical Hadley cell. The westerlies can be quite strong, particularly in the southern hemisphere, where there's less land to disrupt the flow. The region between 40 and 50 degrees south latitude is sometimes called the Roaring Forties because of the strong westerly winds there. Polar easterlies are cold winds that blow from the poles toward about 60 degrees latitude. They're part of the polar cell, where cold, dense air sinks at the poles and flows toward the equator. The Coriolis effect turns these winds so that they blow from the east. The polar easterlies are generally weaker and less consistent than the trade winds or westerlies. Chinook winds, also called Fein winds in other parts of the world, are warm, dry winds that descend the leeward side of mountains. As air is forced up a mountain range, it cools and often releases moisture as precipitation. Once over the crest, the now drier air descends the other side. As it descends, it's compressed by increasing atmospheric pressure, which warms it. The result is a wind that can be dramatically warmer than the surrounding air. Chinook winds east of the Rocky Mountains have been known to raise temperatures by 20 or 30 degrees Fahrenheit in just a few hours. These winds can melt snow rapidly and create increased fire danger. Santa Ana winds in Southern California are hot, dry winds that blow from the desert toward the coast, typically in fall and winter. They occur when high pressure builds over the Great Basin. Air flows from this high pressure area toward lower pressure along the coast, descending from the desert plateau and warming as it compresses. Santa Ana winds can gust over 60 miles per hour and are notorious for spreading wildfires. The combination of low humidity, high winds, and warm temperatures creates extremely dangerous fire conditions. Dust devils are small whirlwinds that form on hot days over dry surfaces. Unlike tornadoes, they form from the ground up rather than descending from clouds. When the ground becomes very hot, it heats the air immediately above it. This hot air wants to rise, but it needs a trigger. A small irregularity in the wind pattern can create a slight rotation. As hot air spirals upward, more air rushes in at the base to replace it, strengthening the rotation. Dust devils are usually harmless, though large ones can cause minor damage. They make visible the otherwise invisible process of hot air rising from heated ground. Microbursts are powerful downdrafts that occur within thunderstorms. They're caused by precipitation-cooled air that becomes denser than the surrounding air and plunges downward. When this air hits the ground, it spreads out in all directions, creating strong winds. Microbursts are particularly dangerous for aircraft during takeoff and landing because the winds can change dramatically over a very short distance. An aircraft flying through a microburst might first encounter a strong headwind, which provides extra lift, then suddenly find itself in a strong downdraft followed by a strong tailwind. This rapid change can cause the aircraft to lose altitude quickly. Atmospheric rivers are long, narrow bands of concentrated moisture in the atmosphere. They form when tropical moisture is channeled by weather patterns into a relatively narrow stream, sometimes only a few hundred miles wide but over 1,000 miles long. When an atmospheric river makes landfall, especially on mountainous coastlines, the result can be torrential rain and heavy mountain snow. The Pacific coast of North America is frequently affected by atmospheric rivers. A single atmospheric river event can drop months' worth of precipitation in just a few days. While this precipitation can be beneficial for water supplies, intense atmospheric rivers can cause devastating floods and mudslides. Lake effect snow occurs downwind of large bodies of water in winter. When cold air moves over a relatively warm lake, it picks up heat and moisture from the lake's surface. This air becomes unstable and rises, forming clouds and producing snow on the downwind shore. The Great Lakes are famous for lake effect snow, with some areas receiving several hundred inches of snow each winter. The snow often falls in narrow bands just a few miles wide, leading to dramatic differences in snowfall over short distances. The urban heat island effect describes how cities tend to be warmer than surrounding rural areas. Buildings, roads, and other infrastructure absorb and retain heat more effectively than vegetation and soil. Dark surfaces like asphalt absorb more solar radiation. Buildings block wind and trap heat. The lack of vegetation means less cooling through evapotranspiration. The result is that cities can be several degrees warmer than nearby rural areas, especially at night. This effect can influence local weather patterns, sometimes enhancing thunderstorm development over or downwind of cities. Drought is an extended period of below normal precipitation that leads to water shortages. Meteorological drought is defined simply by lack of rain, while agricultural drought considers soil moisture and impacts on crops, and hydrological drought focuses on water supplies in streams, reservoirs, and groundwater. Droughts can last months or even years and have numerous causes. Persistent high-pressure systems can block storm tracks, redirecting rain away from affected areas. El Niño and La Niña can shift weather patterns in ways that favor drought in certain regions. Droughts often develop gradually and can be difficult to recognize in their early stages. Flash floods are sudden floods that occur within 6 hours of heavy rainfall. They're called flash floods because they happen quickly, with little warning. Flash floods are particularly dangerous because people are often caught off guard. They're most common in areas with steep terrain, where water runs off rapidly rather than soaking into the ground, and in urban areas where impervious surfaces like roads and parking lots prevent water from infiltrating. It takes remarkably little water depth to cause problems. Just 6 inches of flowing water can knock a person off their feet, and 12 inches can carry away most vehicles. Hail forms in strong thunderstorms when updrafts are powerful enough to keep ice particles suspended in the cloud despite their weight. A hailstone begins as a small ice pellet. As it's carried up and down within the storm by updrafts and downdrafts, it collects layers of ice, growing larger with each cycle. If you cut a hailstone in half, you can often see these layers like the rings of a tree. Eventually, the hailstone becomes too heavy for the updraft to support, and it falls to the ground. Most hail is pea-sized or smaller, but severe storms can produce hail as large as softballs. Large hail can shatter windows, dent cars, damage crops, and injure people or animals caught outside. Rainbows are optical phenomena that occur when sunlight is refracted, reflected, and dispersed by water droplets in the atmosphere. For you to see a rainbow, the sun must be behind you and rain or mist must be in front of you. Sunlight enters a water droplet, slows down, and bends. Different wavelengths of light bend by different amounts, with violet bending most and red bending least. The light then reflects off the back of the droplet and exits, bending again. This double refraction separates the light into its component colors, creating the rainbow. The primary rainbow has red on the outside and violet on the inside. Sometimes a fainter secondary rainbow appears outside the primary rainbow, with colors reversed. This forms when light is reflected twice inside the water droplets. Halos around the sun or moon are caused by ice crystals in high, thin cirrus clouds. These ice crystals act like tiny prisms, refracting light at specific angles. The most common halo is a ring 22 degrees from the sun or moon. Sometimes you can see sundogs, bright spots on either side of the sun, also caused by ice crystals. These optical effects often indicate that a warm front is approaching, bringing a change in the weather within the next day or so. The green flash is a rare optical phenomenon that can occur just as the sun sets or rises. For a very brief moment, the upper rim of the sun appears green. This happens because the atmosphere acts like a prism, refracting different colors of light by different amounts. Green light is refracted more than red or yellow light. At the moment the sun dips below the horizon, only the green light can be seen for an instant before it too disappears. Green flashes are most easily seen over an unobstructed horizon like the ocean on a clear day. Lightning comes in several varieties. Cloud-to-ground lightning is what most people think of when they hear the word lightning. This is when a channel of electricity connects a cloud to the ground. Intracloud lightning occurs within a single cloud and is actually the most common type, though it's often hidden inside the cloud. Cloud-to-cloud lightning jumps between different clouds. Sheet lightning is lightning that illuminates a cloud from within, making the cloud appear to glow. Heat lightning is a term for the glow of lightning from a distant thunderstorm, too far away to hear the thunder. Ribbon lightning occurs when strong winds blow each successive stroke of a lightning flash slightly to the side, creating a ribbon-like appearance. Ball lightning is a rare and poorly understood phenomenon where a glowing sphere of light persists for several seconds. It's been reported for centuries, but scientists still debate exactly how it forms. St. Elmo's fire is a bluish glow that sometimes appears on pointed objects during thunderstorms. It's a form of corona discharge caused by strong electrical fields in the atmosphere ionizing air molecules. Sailors observed St. Elmo's fire on ship masts during storms, and pilots sometimes see it on aircraft wings or windscreens when flying near thunderstorms. Unlike lightning, St. Elmo's fire is a continuous glow rather than a sudden discharge. The calm before the storm is a real phenomenon, not just a figure of speech. Before a severe thunderstorm or tornado, the air can become eerily still. This happens because the approaching storm system is sucking in air from the surrounding area. Once this inflow air reaches the storm, it rises rapidly, creating the updrafts that feed the storm. So the calm isn't a sign that the storm will pass by. It's often a sign that the worst is yet to come. Graupel, also called soft hail or snow pellets, forms when supercooled water droplets freeze onto falling snowflakes. The result is a small, soft ice pellet, white and opaque, easily crushed between your fingers. Graupel bounces when it hits the ground, unlike snow which just lies where it lands. It often falls during winter thunderstorms. Virga is precipitation that falls from a cloud but evaporates before reaching the ground. You can see it as streaks or curtains of rain or snow hanging beneath a cloud. Virga is common in dry climates where the air near the ground has low humidity. The precipitation simply evaporates as it falls through this dry air. Virga can cool the air beneath a cloud and sometimes triggers gusty winds as the cooled air descends rapidly. Mammatus clouds are pouch-like structures that hang beneath the base of a cloud, usually a cumulonimbus. They form in sinking air, which is unusual since clouds typically form in rising air. The pouches develop when ice crystals in the upper part of the cloud begin to melt and sink, creating a lumpy appearance. While mammatus clouds often accompany severe weather, they themselves are not dangerous. They're simply a sign of the turbulent atmospheric conditions present. Lenticular clouds are smooth, lens-shaped clouds that form in stable air on the downwind side of mountains. They look almost like flying saucers and remain stationary even though air is constantly flowing through them. They form when moist air is forced up and over a mountain range, cooling as it rises. If the air is stable, it oscillates up and down in waves downwind of the mountain. Clouds form at the crest of each wave where the air is coolest, and they evaporate in the troughs where the air warms. The clouds don't move because they're forming and dissipating continuously in the same location. Kelvin-Helmholtz clouds look like breaking ocean waves in the sky. They form when there's strong wind shear, meaning wind speed or direction changes rapidly with altitude. If a layer of fast-moving air flows over slower-moving air, and the atmosphere is stable enough, waves can form at the boundary between the two layers. These waves can break just like ocean waves, creating the distinctive curling pattern. Kelvin-Helmholtz clouds indicate turbulence and are a warning sign to pilots. Noctilucent clouds are the highest clouds in Earth's atmosphere, forming about 50 miles above the surface in the mesosphere. They're so high that they're made of ice crystals, even though the mesosphere is generally too dry and thin for cloud formation. Scientists believe these ice crystals form on tiny meteor dust particles. Noctilucent clouds are only visible during twilight, when the sun has set at the ground level but still illuminates these high clouds from below the horizon. They appear as thin, wispy, bluish or silvery clouds. They're most commonly seen at high latitudes during summer. Crepuscular rays are shafts of sunlight that appear to radiate from the sun when clouds partially block it. They're most commonly seen at sunrise or sunset when the sun is low on the horizon. The rays are actually parallel columns of sunlight and shadow, but perspective makes them appear to diverge from the sun. Anticrepuscular rays are the opposite phenomenon, appearing as rays converging toward the antisolar point, the spot directly opposite the sun in the sky. The green ray is different from the green flash. It's a vertical band of green light that sometimes appears above the sun just as it sets. Like the green flash, it's caused by atmospheric refraction, but it requires specific atmospheric conditions, including a temperature inversion, to create a duct that can trap and bend green light. Moonbows are rainbows created by moonlight instead of sunlight. They're much rarer than solar rainbows because moonlight is much dimmer than sunlight. Moonbows are usually too faint for the human eye to perceive color, so they often appear white or pale. They're most likely to be seen during or just after rain, on nights when the moon is bright and high in the sky. Waterspouts are tornadoes that form over water. Most are relatively weak and form in fair weather, developing beneath towering cumulus clouds. They're most common in tropical and subtropical waters. These fair weather waterspouts form from the surface up, beginning as a dark spot on the water and a spiral pattern of light and dark bands on the water surface. A funnel gradually extends downward from the cloud base. They typically last about 10 to 15 minutes and rarely move on shore. Tornadic waterspouts are true tornadoes that form over water or move from land to water. These are much more dangerous and can have wind speeds exceeding 100 miles per hour. Fire whirls, sometimes called fire tornadoes, are rotating columns of air associated with intense fires. They form when rising hot air from a fire begins to rotate, often due to uneven heating or interaction with wind patterns. Fire whirls can have winds strong enough to carry burning debris considerable distances, spreading the fire. They can reach heights of several hundred feet and last minutes or even hours if conditions are right. Steam devils are small, rotating columns of steam-saturated air that form over bodies of water when cold air moves over much warmer water. They look like small tornadoes made of steam and typically last only a few minutes. They're most common over lakes and rivers on cold mornings in late fall and early winter. Gustnadoes are weak, short-lived whirlwinds that form along the gust front of a thunderstorm. They're caused by wind shear along the gust front and don't extend from the cloud base to the ground like true tornadoes. Gustnadoes can still produce damaging winds and are often mistaken for tornadoes. A macroburst is a large downdraft from a thunderstorm, similar to a microburst but larger, affecting an area more than 2.5 miles across. Macrobursts can produce damaging straight-line winds over a large area and are sometimes mistaken for tornado damage. Squall lines are organized lines of thunderstorms that can extend for hundreds of miles. They often form along or ahead of cold fronts and can produce severe weather including damaging winds, hail, and tornadoes. A particularly intense squall line is called a derecho, which produces widespread damaging winds over a long distance, sometimes exceeding 400 miles. Supercells are the most severe type of thunderstorm, characterized by a rotating updraft called a mesocyclone. While supercells make up only about 10% of thunderstorms, they produce a disproportionate amount of severe weather. Most strong and violent tornadoes come from supercells, as do the largest hailstones and most destructive winds. A supercell can last for hours and travel hundreds of miles. The anvil of a thunderstorm is the flat, spreading top of a mature cumulonimbus cloud. It forms when the rising air in the storm reaches the tropopause, the boundary between the troposphere and stratosphere. Here the air encounters a stable layer and can't rise further, so it spreads out horizontally, forming the characteristic anvil shape. The anvil can extend for miles downwind from the main storm. Wall clouds are localized, persistent lowerings from the base of a thunderstorm. They form in the rain-free area of a severe thunderstorm, where the main updraft is located. Wall clouds are significant because they're the area where tornadoes are most likely to form, though most wall clouds don't produce tornadoes. When a wall cloud begins to rotate persistently, it indicates that a tornado may be developing. Shelf clouds are dramatic, low, horizontal clouds that appear along the leading edge of a thunderstorm. They form as cold air from the storm's downdraft spreads out along the ground, lifting warm, moist air ahead of it. Shelf clouds can look menacing, stretching across the entire horizon, but they themselves don't produce tornadoes. They do signal that strong winds and heavy rain are imminent. Roll clouds are long, horizontal, tube-shaped clouds that appear to roll about a horizontal axis. They're relatively rare and form when a gust front or sea breeze lifts moist air, creating a wave. If the air behind this wave is drier, a single roll cloud can form, disconnected from other clouds. Roll clouds can be hundreds of miles long and travel at speeds up to 35 miles per hour. Morning glory clouds are spectacular roll clouds that regularly form over northern Australia, particularly in the Gulf of Carpentaria region during September and October. They can be up to 600 miles long and travel at speeds of 35 miles per hour. Multiple morning glory clouds can appear in succession, with up to 10 arriving one after another. Glider pilots seek them out because of the strong updrafts associated with them. Contrails are the white streaks that form behind high-flying aircraft. They're artificial clouds made of ice crystals that form when hot, humid exhaust from jet engines meets the cold, low-pressure air of the upper atmosphere. If the air is humid enough, contrails can persist for hours and spread out to form cirrus-like clouds. If the air is dry, contrails dissipate quickly. Contrails can actually affect local weather slightly by reflecting sunlight during the day and trapping heat at night. Hoarfrost is different from regular frost. While regular frost forms from water vapor condensing directly onto cold surfaces, hoarfrost forms when water vapor directly deposits onto surfaces that are already below freezing. The result is feathery, delicate ice crystals that grow outward from surfaces. You might see hoarfrost on tree branches, fences, or grass on very cold mornings. It creates a beautiful, winter wonderland appearance. Rime ice forms when supercooled water droplets freeze instantly on contact with objects. This happens when fog or low clouds are present and temperatures are below freezing. Rime ice can build up dramatically on the windward side of objects, creating fantastical shapes. Mountains are particularly prone to rime ice formation. Unlike glaze ice, which is smooth and clear, rime ice is white and opaque with a rough, crystalline texture. Black ice is a thin, nearly invisible coating of ice on surfaces, particularly roads. It forms when the road's surface temperature is below freezing and rain falls, or when melting snow or rain refreezes. It's called black ice not because it's black, but because it's so transparent that you can see the dark pavement through it. This makes it extremely dangerous because drivers often don't see it until their vehicle is sliding. Graupel, soft hail, and sleet are all forms of frozen precipitation, but they form differently. Graupel forms when supercooled water droplets freeze onto a snowflake. Sleet forms when raindrops freeze into ice pellets as they fall through a layer of freezing air. And soft hail is another term for graupel. These distinctions matter to meteorologists but often get confused in everyday conversation. Snow squalls are brief but intense bursts of heavy snow accompanied by strong winds. They can reduce visibility to near zero within minutes and create hazardous travel conditions. Snow squalls are often associated with strong cold fronts and can produce several inches of snow in a short period. The sudden onset and rapidly changing conditions make snow squalls particularly dangerous. Whiteout conditions occur when falling or blowing snow reduces visibility to near zero. During a whiteout, the horizon disappears, and it becomes impossible to distinguish between the ground and sky. This is extremely disorienting and dangerous for travelers. Whiteouts can occur during blizzards, or when strong winds pick up snow that's already on the ground. Blizzards are severe winter storms defined not just by snowfall but by strong winds and reduced visibility. In the United States, a blizzard is officially defined as a storm with winds of at least 35 miles per hour and visibility of less than a quarter mile for at least 3 hours. It doesn't even have to be snowing during a blizzard. If winds are strong enough to blow existing snow around, meeting these criteria, it's still a blizzard. The combination of cold, wind, and poor visibility makes blizzards life-threatening. Ground blizzards occur when no snow is falling, but strong winds pick up snow from the ground, reducing visibility. These can occur under clear skies and catch travelers off guard. The danger is just as real as in a regular blizzard because visibility can drop to zero within moments. Ice storms occur when freezing rain accumulates on surfaces, coating everything with ice. Just a quarter inch of ice can bring down tree branches and power lines. Half an inch is considered a major ice storm, capable of causing widespread damage. Trees weighted down with ice can take down power lines, leaving areas without electricity for days or even weeks. Ice storms are most common in a narrow geographical zone where conditions are just right for freezing rain to occur. The Alberta Clipper is a type of fast-moving winter storm system that forms in the province of Alberta, Canada, and then races southeastward across the United States. These storms typically don't produce large amounts of snow, but they bring bitter cold air and strong winds. They're called clippers because of their speed, crossing the country in just a few days. Nor'easters are powerful storms that affect the east coast of the United States, particularly from North Carolina to New England. They're named for the strong northeast winds that blow in from the ocean ahead of the storm. Nor'easters can occur at any time of year but are most common and most intense during winter. They can bring heavy snow, rain, strong winds, and coastal flooding. The most intense nor'easters can produce blizzard conditions and are sometimes called bomb cyclones when they intensify rapidly. Bomb cyclones, more formally called explosive cyclogenesis or bombogenesis, occur when a storm's central pressure drops rapidly, at least 24 millibars in 24 hours. This rapid intensification produces a very strong storm with powerful winds. The term might sound sensational, but it's an actual meteorological term that's been used since the 1950s. Atmospheric pressure is measured in various units. Millibars and hectopascals are the same thing and are commonly used in meteorology. Inches of mercury is another common unit, particularly in the United States. Standard sea level pressure is about 1,013 millibars, 29.92 inches of mercury, or 1 atmosphere. The lowest sea level pressure ever recorded was during Typhoon Tip in 1979, which reached 870 millibars. That's about 15% lower than standard pressure. Barometers measure atmospheric pressure and can help predict weather changes. When pressure is falling, it often indicates that a storm is approaching. Rising pressure typically means improving weather. Rapid pressure changes indicate that significant weather changes are imminent. Aneroid barometers use a small, flexible metal box that expands and contracts with pressure changes. Mercury barometers use a column of mercury, with pressure changes causing the mercury level to rise or fall. The altimeter in aircraft is essentially a barometer calibrated to show altitude. As an aircraft climbs, atmospheric pressure decreases in a predictable way, so by measuring pressure, the altimeter can determine altitude. Pilots must adjust their altimeters for local pressure variations to ensure accurate altitude readings. Density altitude is an important concept for pilots. It's the altitude at which the air density would equal the current air density in the standard atmosphere. Hot weather and high humidity both decrease air density, resulting in high-density altitude. This reduces aircraft performance because engines produce less power and wings generate less lift in less dense air. On a hot summer day at a high-elevation airport, density altitude can be several thousand feet above the actual elevation. Temperature and humidity affect air density. Warm air is less dense than cold air because the molecules have more energy and spread out. Humid air is less dense than dry air, which surprises many people. This is because water vapor molecules are lighter than nitrogen and oxygen molecules. When water vapor displaces these heavier molecules, the overall density decreases. Relative humidity is the amount of water vapor in the air compared to the maximum amount the air could hold at that temperature. Warm air can hold much more water vapor than cold air. This is why relative humidity often rises at night even though no moisture is being added to the air. As temperature drops, the air's capacity to hold moisture decreases, so the same absolute amount of moisture represents a higher percentage of capacity. The dew point is the temperature to which air must cool for it to become saturated with water vapor. It's a more reliable measure of moisture content than relative humidity because dew point doesn't change with temperature. A dew point of 65 degrees Fahrenheit or higher feels humid and uncomfortable. Dew points above 70 degrees are oppressive. In dry climates, dew points can be in the 20s or 30s, feeling very dry and comfortable. The highest dew points occur in tropical regions and can occasionally reach the mid-80s. The heat index combines temperature and humidity to describe how hot it actually feels. High humidity makes hot weather feel even hotter because it reduces the evaporation of sweat, which is the body's primary cooling mechanism. A temperature of 95 degrees Fahrenheit with 60% humidity feels like 112 degrees. At heat index values above 103 degrees, heat disorders become likely with prolonged exposure and physical activity. Wind chill describes how cold it feels when wind is factored in. Wind removes the thin layer of warm air near the skin, making you feel colder than the actual air temperature. A temperature of 0 degrees Fahrenheit with a 15-mile-per-hour wind feels like -19 degrees. At these extreme wind chill values, frostbite can occur in minutes on exposed skin. Frostbite is the freezing of skin and underlying tissues. It most commonly affects fingers, toes, nose, and ears. In frostbite, ice crystals form in and between cells, damaging them. Blood vessels also constrict, reducing blood flow. Mild frostbite, called frostnip, affects only the outer skin and doesn't cause permanent damage. Severe frostbite can penetrate deep into tissues and may require amputation. Hypothermia occurs when body temperature drops below 95 degrees Fahrenheit. It happens when heat loss exceeds heat production. Mild hypothermia causes shivering and confusion. As body temperature continues to drop, shivering stops, muscles stiffen, and consciousness is lost. If untreated, hypothermia is fatal. Hypothermia can occur even in relatively mild temperatures if someone is wet and exposed to wind. Heat exhaustion occurs when the body loses excessive water and salt through sweating. Symptoms include heavy sweating, weakness, dizziness, nausea, and headache. If not treated, heat exhaustion can progress to heat stroke, which is a medical emergency. In heat stroke, the body's temperature regulation fails, body temperature rises above 104 degrees, and sweating often stops. Heat stroke can cause organ damage and death if not treated immediately. Dehydration occurs when fluid loss exceeds fluid intake. Even mild dehydration can cause fatigue, headaches, and difficulty concentrating. In hot weather, fluid needs can increase dramatically. By the time you feel thirsty, you're already mildly dehydrated. The color of urine is a good indicator of hydration status. Pale yellow indicates good hydration, while dark yellow or amber indicates dehydration. Lightning safety is critical because lightning kills dozens of people each year and injures hundreds more. When thunder roars, go indoors is the mantra. If you can hear thunder, you're close enough to be struck by lightning. The 30-30 rule is helpful. If the time between seeing lightning and hearing thunder is 30 seconds or less, seek shelter. Then wait at least 30 minutes after the last thunder before resuming outdoor activities. If caught outside during a thunderstorm with no shelter available, avoid high ground, isolated trees, and metal objects. Crouch low but don't lie flat, as lying flat makes you a larger target for ground current if lightning strikes nearby. Lightning can strike the same place multiple times. Tall structures are frequently hit multiple times during a single storm. The Empire State Building is struck about 25 times per year. Lightning rods work by providing a preferred path for lightning to reach the ground safely, protecting structures. Thunder can be heard from about 10 to 15 miles away under good conditions, though strong winds, heavy rain, and other factors can reduce this range. Sometimes lightning is too far away for thunder to be heard. This is the heat lightning mentioned earlier. It's just ordinary lightning from a distant storm. Fulgurites are natural tubes of glass formed when lightning strikes sand or rock. The extreme heat of the lightning bolt, which can exceed 30,000 degrees Fahrenheit, melts the material. When it cools, it solidifies into a tube of glass following the path of the lightning through the ground. Fulgurites can be just a few inches long or extend several feet underground. They're hollow, often branching, and extremely fragile. Aurora borealis, the northern lights, and aurora australis, the southern lights, are atmospheric phenomena caused by solar wind interacting with Earth's magnetic field. Charged particles from the sun are funneled toward the poles by Earth's magnetic field. When these particles collide with oxygen and nitrogen in the upper atmosphere, they excite these atoms, causing them to emit light. Oxygen produces green and red light, while nitrogen produces blue and purple. Auroras typically occur at altitudes between 60 and 200 miles. They're most commonly seen near the poles but can occasionally be visible at lower latitudes during strong solar storms. The colors in auroras depend on which gases are involved and at what altitude the collisions occur. Green, the most common aurora color, is produced by oxygen at lower altitudes, around 60 to 150 miles. Red auroras are produced by oxygen at higher altitudes, above 150 miles. Blue and purple auroras are produced by nitrogen. The intensity and position of auroras vary with solar activity. The sun goes through an 11-year cycle of activity, and auroras are most frequent and vivid during solar maximum. Solar flares are massive explosions on the sun's surface that release enormous amounts of energy. When directed toward Earth, the charged particles from a solar flare can reach our planet in 1 to 3 days. Strong solar flares can interfere with radio communications, damage satellites, and even disrupt power grids. The Quebec blackout of 1989 was caused by a solar storm that induced currents in power lines, overloading transformers. The magnetosphere is the region around Earth where our planet's magnetic field dominates over the solar wind. It extends about 60,000 miles on the side facing the sun and trails out much farther on the opposite side. The magnetosphere shields Earth from most of the solar wind, which would otherwise strip away our atmosphere. Without this protection, Earth would be as barren as Mars. Cosmic rays are high-energy particles, mostly protons, that bombard Earth from space. Most come from distant supernovae, exploded stars. Earth's magnetic field and atmosphere protect us from most cosmic rays, but some reach the surface, especially at high altitudes and high latitudes where the magnetic field provides less shielding. Cosmic rays can actually affect cloud formation in the atmosphere, though the mechanism and significance are still debated among scientists. Climate is the long-term average of weather patterns, typically calculated over 30 years or more. While weather describes conditions at a specific time and place, climate describes the typical conditions in a region over long periods. A region's climate is determined by factors including latitude, altitude, proximity to water bodies, prevailing winds, and ocean currents. Climate zones are large areas with similar climate characteristics. The main climate zones are tropical, dry, temperate, continental, and polar. Within these broad categories are many subcategories. The Köppen climate classification system, developed in the early 1900s, divides the world into 5 main climate groups based on temperature and precipitation patterns, with numerous subdivisions. This system is still widely used today. Tropical climates are found near the equator and are characterized by warm temperatures year-round and significant rainfall. There are no distinct seasons in terms of temperature, though there may be wet and dry seasons. Tropical rainforests receive rain throughout the year, while tropical savannas have distinct wet and dry seasons. Dry climates receive little precipitation and have high evaporation rates. Deserts receive less than 10 inches of rain per year. Some deserts, like the Atacama in Chile, can go years without measurable rain. Semi-arid steppes receive slightly more precipitation than deserts, typically 10 to 20 inches per year, enough to support grasslands but not forests. Temperate climates have moderate temperatures and distinct seasons. Summers are warm and winters are cool but not extreme. Most temperate regions have relatively even precipitation throughout the year. The temperate climate zone includes Mediterranean climates with wet winters and dry summers, humid subtropical climates with hot, humid summers, and oceanic climates with mild temperatures and frequent cloud cover. Continental climates are found in the interior of large land masses, far from the moderating influence of oceans. They're characterized by large temperature ranges between summer and winter. Summers can be hot while winters are very cold. Precipitation is typically moderate, with most falling during the warmer months. Polar climates are extremely cold year-round. Even the warmest month averages below 50 degrees Fahrenheit. The polar regions receive little precipitation, technically making them deserts, though they're covered with ice and snow because temperatures are so cold that what little precipitation falls doesn't melt. The polar climate includes both ice cap climates where all months average below freezing, and tundra climates where at least one summer month averages above freezing, allowing some vegetation to grow. Mountain climates vary with altitude. Temperature decreases with elevation at a rate of about 3.5 degrees Fahrenheit per 1,000 feet. This means that climbing a mountain is like traveling toward the poles. You pass through different climate zones as you gain altitude. Mountains also create their own local weather patterns. They block air masses, create precipitation on windward slopes, and produce dry conditions on leeward slopes in a phenomenon called the rain-shadow effect. The rain-shadow effect occurs when moist air is forced up a mountain range. As it rises, it cools and releases moisture as precipitation on the windward side. By the time the air descends on the leeward side, it's lost most of its moisture. As it descends and warms, it becomes even drier, creating arid conditions. The western United States provides many examples. Moisture-laden air from the Pacific drops rain and snow on the western slopes of the Sierra Nevada. But the air that descends into Nevada is dry, creating desert conditions. Ocean currents play a major role in determining climate. Warm currents like the Gulf Stream carry warm water from the tropics toward the poles, warming coastal regions along their path. Cold currents like the California Current bring cold water from higher latitudes toward the equator, cooling coastal regions. The Gulf Stream keeps Western Europe much warmer than regions at similar latitudes. London, England, is farther north than Calgary, Canada, but has a much milder climate thanks to the Gulf Stream. Thermohaline circulation, sometimes called the ocean conveyor belt, is a global-scale ocean circulation driven by differences in water density, which depends on temperature and salinity. Cold, salty water is denser and sinks, while warm, fresh water is less dense and floats. This creates a slow-moving circulation that connects all the world's oceans. Water that sinks in the North Atlantic may not resurface for 1,000 years. This circulation helps redistribute heat around the planet and influences climate on a global scale. Upwelling occurs when winds push surface water away from a coast and deeper water rises to replace it. This deep water is cold and rich in nutrients that have accumulated in the depths. Upwelling zones are among the most biologically productive areas in the ocean because the nutrients support abundant plankton growth, which feeds fish and other marine life. Major upwelling zones include the coasts of Peru, California, and Northwest Africa. Tides are the rise and fall of sea level caused by the gravitational pull of the moon and sun. The moon has a stronger effect than the sun because although the sun is much more massive, the moon is much closer. Tides occur in a complex pattern, with most coasts experiencing 2 high tides and 2 low tides each day. Spring tides, which occur during new and full moons when the sun and moon align, have the greatest range between high and low tide. Neap tides, which occur during quarter moons when the sun and moon are at right angles, have the smallest range. Tides can influence weather along coasts by affecting ocean temperatures and moisture availability. Sea surface temperatures have a profound effect on weather and climate. Warm ocean water provides energy for hurricanes and can increase rainfall in coastal areas. Cold ocean water tends to stabilize the atmosphere, suppressing thunderstorm development. The temperature contrast between ocean and land drives sea breezes and affects larger-scale weather patterns. Evaporation is the process by which liquid water becomes water vapor. It requires energy, which comes from the sun or surrounding environment. Evaporation rates depend on temperature, humidity, wind speed, and surface area. Hot, dry, windy conditions promote rapid evaporation. Cool, humid, calm conditions slow evaporation. Most of the water vapor in the atmosphere comes from evaporation from oceans. Transpiration is evaporation from plants. Water absorbed by plant roots eventually evaporates from tiny pores called stomata, mostly on the undersides of leaves. Transpiration serves several functions for plants, including cooling and nutrient transport. In vegetated areas, transpiration can account for a significant portion of moisture entering the atmosphere. The combined process of evaporation and transpiration is called evapotranspiration. Condensation nuclei are tiny particles in the atmosphere on which water vapor condenses to form cloud droplets. Without these particles, air could become supersaturated with water vapor without forming clouds. Natural condensation nuclei include sea salt crystals, dust, pollen, and particles from volcanic eruptions and wildfires. Human activities also produce condensation nuclei through combustion and industrial processes. Clouds are classified by their altitude and appearance. High clouds, found above 20,000 feet, include cirrus, cirrostratus, and cirrocumulus. They're composed of ice crystals due to the cold temperatures at these altitudes. Middle clouds, between 6,500 and 20,000 feet, include altostratus and altocumulus. Low clouds, below 6,500 feet, include stratus, stratocumulus, nimbostratus, and cumulus. Clouds that span multiple altitude ranges, like cumulonimbus, are called clouds with vertical development. Cloud seeding is an attempt to modify weather by dispersing substances into clouds. Silver iodide is commonly used because its crystalline structure resembles ice, allowing it to serve as condensation nuclei. The theory is that seeding clouds with extra nuclei will enhance precipitation. Cloud seeding has been used to try to increase rainfall, reduce hail damage, and dissipate fog. However, its effectiveness remains controversial because it's difficult to prove whether precipitation would have occurred anyway. The water cycle describes the continuous movement of water through the Earth system. Water evaporates from oceans, lakes, and land surfaces, becoming water vapor in the atmosphere. This water vapor eventually condenses into clouds. Precipitation falls from clouds back to the surface. Some precipitation infiltrates into the ground, some flows over the surface as runoff, and some returns directly to the atmosphere through evaporation and transpiration. Groundwater may flow underground for long distances before emerging in springs or being absorbed by plant roots. Eventually, most water makes its way back to the oceans, completing the cycle. Residence time is the average time a water molecule spends in different parts of the water cycle. Water in the atmosphere has a residence time of about 9 days. Water in rivers moves through quickly, with an average residence time of 2 weeks. Water in lakes can remain for years or even decades. Groundwater can have residence times of hundreds or thousands of years. Water in glaciers and ice sheets can remain frozen for tens of thousands or even hundreds of thousands of years. Water in the deep ocean circulates slowly, with residence times of over 1,000 years. Watersheds, also called drainage basins, are areas of land that drain to a common outlet, like a river, lake, or ocean. The boundary of a watershed is called a divide. Rain falling on one side of a divide flows to one body of water, while rain falling on the other side flows to a different body of water. Watersheds can be nested. Small watersheds combine to form larger ones. The Mississippi River watershed, for example, drains about 40% of the continental United States, collecting water from 31 states and 2 Canadian provinces. Floods are natural events that occur when water overflows the natural or artificial banks of a waterway. They can be caused by heavy rainfall, rapid snowmelt, storm surge from hurricanes, or dam failure. Riverine floods develop slowly as rain over a large watershed accumulates in rivers. Flash floods develop rapidly, typically within 6 hours of heavy rain. Coastal floods are caused by storm surge, when strong winds push ocean water onto land. Flooding is the most common and costly natural disaster. Flood stages describe river levels in relation to flooding. Action stage is when a river reaches a level where preparations for possible flooding should begin. Flood stage is when water begins to overflow the banks or cause some damage. Moderate and major flood stages indicate progressively more severe flooding. Different locations along a river have different flood stages because channel characteristics vary. 100-year floods and 500-year floods are statistical concepts describing flood severity. A 100-year flood has a 1% chance of occurring in any given year. This doesn't mean such a flood happens only once per century. It's possible to have 2 100-year floods in consecutive years, though it's unlikely. These terms are somewhat misleading because they imply predictability that doesn't exist. Climate change, land use changes, and other factors can alter flood frequencies. Now let your mind rest with these patterns of the atmosphere. The endless dance of air and water, heat and cold, always moving, always changing, creating the weather that shapes our world. The atmosphere continues its work even as you sleep, winds flowing, clouds forming and dissipating, the water cycle turning. These processes have operated for billions of years and will continue long into the future. Rest now, knowing that the patterns of weather follow understandable principles, that chaos has order, that change is constant, and that tomorrow the sun will rise on new weather, new patterns, new possibilities. Sleep peacefully.